Now, can you see me flip it?
Yeah, that works.
Okay. All right. So these were these three chapters I was referring to. So chapters on optimization, high performance computing, and the examples in all likelihood we will skip this year, but these are less important, right? So the course would also stand without those. So you shouldn't be too worried about this.
Is it maybe possible to send us the PowerPoint presentation for us to see?
The remaining chapters,
yeah.
We can do that.
Okay, thank you.
So in the machine learning chapter, I want to cover the following things here. I want to briefly introduce and motivate the application of machine learning to this. Then discuss the machine learning, the electronic Schrodinger equation in compound space. Then discuss some performances on quantum properties. And then there are three chapters which have as topics certain strategies, if you wish, that have in the past been shown to improve machine learning models for quantum properties in compound space. So I'll cover these as well. Now, this chapter is based on material which is quite new, so we will be using original literature to a large extent also naturally from my group. This is, you will be presented with something rather biased in some sense, right? That is unfortunately often the case when rather new material is taught. As time progresses, right, there will be textbooks and so on which will cover the field more broadly. There has been a lot of activity going on in the field over recent years, so this chapter could also be extended into much more. So I'll try to give this sort of selected overview, and I'll try to also mention where appropriate other approaches. You should not expect a comprehensive, complete sort of treatment of the subject. Coming to the introduction, right? I go through this quite quickly because I'm pretty sure you're aware of this. So in nowadays, machine learning has become a part of everyday life. Here's an example on Amazon. You find a book you like, and then the AI will propose other books to you. And these propositions are based on machine learning algorithms, right? You are probably aware also of the challenge of autonomous driving. This is also happening right now. I think it's quite exciting. Volvo or Tesla have been promising the fully autonomous car drive for a while now, but lately, just most recently, they have reconfirmed that they plan to really now make this happen within this or next year. Another example that's also gaining increasingly more traction is the application of machine learning to signal processing. And one of the most fascinating things are these brain-computer interfaces, right? If you can interpret brain signals with such an interface, of course, you could realize a long-standing dream of humanity. And this was part, of course, in the science fiction literature, or of famous movies such as The Matrix, where the brain is directly coupled to the machines, right? And you experience a simulated reality. Now, here's an example from a collaborator of mine, Katja Hansen, playing a pinball machine without touching the machine. Okay. So I don't know how well she plays, but apparently she played as well with this interface as she would play with her own hands. This is, of course, fantastic if you happen to be handicapped and if you don't have control over your bodily function. If you can then have such an interface, you could really direct robotic devices and gain an entirely new quality of life. Now, there is a cautionary word to this, and I think this is an elephant in the room, and elephants in the rooms are quite common, right, in society. So I show here one elephant in the room for the politically left-leaning people and one for the politically right-leaning people. This is something, of course, that is shouldn't be surprising. And the elephant in the room is that these regression, these surrogate models, right? These are statistics models, and so and they don't always work so well. Okay, so you should, of course, as a good scientist, question the performance and the validity of any model anybody submits to you, and that includes machine learning, of course. And it is quite straightforward to produce failures, right? And so this is, of course, not to spoil the game, but or not to be the party pooper, but this is, of course, part of the scientific progress, right? We are always thrilled to see new models and new ansatz, but then, of course, we want to see how far it works. What is the performance? So you need to agree on benchmarks and test things and compare them to the literature to have a meaningful idea of what really the context is in terms of usefulness. And so this is something, of course, we need to do then with these machine learning models as well. So here, just for fun, this is a result. It is already a while ago. I wonder how this would change if I did it today. But yeah, nearly 10 years ago or so, I uploaded my image to Google and did an image search, and these people apparently look like me. And so this is right. This is sort of the problem with statistics, right? This is a hard problem, of course, the similarity. And if you upload a picture of you, your intent typically is to find somebody who looks like you and not somebody who happens to have the same jacket or the same background in the image, right? But the machine does not know this, right? And it will make a guess on how the similarity should be measured. And so that guess can be very ill-informed, of course. Now, this is related to the obvious, well-known wisdom that correlation is only a necessary but not a sufficient criterion for causal relation. And Tversky and Kahneman are well-known in discussing these things in the societal context, right? For rational discussions, decisions. And there's also a nice mathematician slash finance person, Nassim Taleb. He's a professor at NYU in the economics department, but he wrote a couple of popular books on statistics and what you can do with it. And this is one of his first books, this Fooled by Randomness, which is quite an entertaining read, I would say. So this has, of course, nothing to do with materials, but a lot of with statistics and daily life. Now, this plot of usage of Internet Explorer versus murder rate is also a classic, right? Obviously these two shouldn't be directly related, but they could have a joined cause, right? So there are multiple reasons why you actually can have a correlation, right? And having a joint cause could be is often a very good reason. So let me propose a joint cause, right? It could be, for instance, that in this time span from 2006 to 2011, prosperity grew a lot, and so prosperity then means that people are wealthy enough to migrate from Microsoft to Apple, and that people kill each other less, right? So maybe that's a good cause, right? So it's just because there's no obvious causal link doesn't mean that there's no relation at all. So this common cause. There could also be simply an identity relationship. It could also be chance, right? So one thing you see here is a scale which goes from 45 to 75%, right? Here you see a scale going from 17,000 to 14,000, right? So basically somebody has been playing with the units of these axes, right? And you can also play with the axes, with the x-axis, right? They don't have to necessarily align in terms of time, right? You could have murder rate decay in different time periods than Internet Explorer decay, right? And so if you're allowing for these guys being adjustable, right, chances are that you will find some time segment in the historic past where murder decay matches very well Internet Explorer usage changes, right? In any certain time period. So I think that's these are things one has to be very, very much aware of when using statistical models, right? Now there's also a bias component, and that I come to that later on. So here's a silly correlation. There's a funny internet homepage called Spurious Correlations. I don't know. Yeah, here's this. You can look this up. There's tons of spurious charts. Also, this one, the divorce rate in Maine versus consumption of margarine. Great correlation, right? So my father is a medical doctor, and I often make fun of him because in these medical sciences, they talk about scatter plots and correlations with correlation coefficients close to 0.5, and they try to interpret some meaning in there, right? So this is then in certain sciences, such a correlation coefficient would be very impressive. This one, of course, is a little bit less, but this is so yeah, it's quite an entertaining thing, and I think once you look at a couple of figures like this, it becomes very obvious that correlation is not enough. Now we can push this a little bit further. Here you have a scatter plot where you might think this is a good correlation, right? There's now a demonstration on how you can generate chance or fortuitous or not fortuitous, but really by chance you can. It's not even chance, right? Basically, it's a random thing. So using random data, you can generate scatter plots which look like correlations, right? So you might have the idea that the y and the x axes have some relationship with each other. Now, this is not really true. This is coming from 500 random draws for 3 variables, right? X, Y, and Z. And so the normal distribution here has a mean of 10 and a width of 1. And so they each X and Y, they get divided by C. Z has a mean of 30. And so 10 by 30 is roughly 0.3, right? So you see the values in this range, right? And the squeezing by the same number, the division by the same number results in the squeezing of this data, right? And so, but all numbers are random here. So there's zero correlation. So we cannot infer a causal relationship, but if there is a causal relationship, of course, there must be a correlation, right? So absence of correlation is actually also meaningful in an exclusion sense, right? Little side remark: if you go on the world in data and you plot countries with vaccination rates versus countries with deaths of COVID, it's very hard to see a correlation. So what this means, we don't know. Excuse me. I think it's very important to be very open-minded and to question the presentation and the analysis of these data sets when it comes to our kind of science. Now here is an example on bias. If you arrange a couple of black dots in this fashion, and you then start adding black dots in the center, right, successively, at some point your brain decides that these dots are not really arranged in incoming arrays, but rather in circles, right? And, excuse me. I thought I had switched this off. And your brain did not really ask you about when to do this, right? It's basically in the neural net of your brain, you have some threshold that some algorithm that does it for you, and this is unconscious, right? You didn't decide on that threshold, right? It seems to be typically that we use a distance measure, right? So if the distance to the dots in the same array is smaller than the distance to the neighboring dots at a constant radius, then you decide this is still an array. And if it's larger, then you decide it's a circle. Most people operate like this, but we don't know. I mean, maybe there's some people who don't simply take the distance, but they also figure in the length of the whole thing or whatever, right? So it's not a rational decision, right? So humans we are typically quite poor at doing statistics, right? And a famous example for this is the Monty Hall dilemma. This was a host show in the US, and the host presented often participants in the show with 3 doors, right? And he promised that behind one door there's going to be some kind of a prize award, a car or a house or boat or whatever. And the question then is, the participants were asked to pick a door, right? You basically had the case where you have 2 kind of decisions. So the guest would open one door, let's say door number 1, and there was nothing behind it. Okay, and then the question was, Okay, once you've opened this, which door, once you open this and you don't see it, right? Would you take either one of these doors, right? Should you change the door or not? And so this is because one door was opened, it changed the probability on the other two, right? And so this is once you open a door, so now it's shown for door number 3, right? Once you open the door, the host would ask the guest, would you now take either door 2 or either door 1, right? And the probability of your prize being in either of these two was 2/3, right? And then because you know that this door was eliminated, there's a goat behind and not the real award. The question is, should you now take door 1 or door 2 to go for the award, right? And the solution is, of course, that you should take door 2, because door 2 still carries this 2/3 probability, right? So now the 1/3 probability, because this door was eliminated, carries over to door 2, while door 1 still has only 1/3 probability. Okay. So this is something where most host show guests did not succeed, right? They basically said they didn't go for the more probable door, so this demonstrates how poor our intuition is in terms of statistics. Now, another example is, which is very common, is that we underestimate the dimensionality of the problem. So if you're presented with such data here, you might make the statement that there's no relationship between them. It's just a random sampling. But in fact, you can, by adding another dimension, right, there could be a very strong relationship between these data points, right? And so this neglect of dimensionality is something also that we struggle with a lot. Another nice example is this Penrose triangle. I don't know if you know about this. So Roger Penrose is a mathematician in Cambridge, I think, who just recently got the Nobel Prize in physics, not for this, but for other work. But anyhow, he discussed the geometry of such objects. And here you see the Penrose triangle in the real world. Okay, and there's a picture, and this does not seem possible, right, to be realized in the real world, right? Yet you see it here on this picture, right? And the reason is simple. This picture is a 2D projection of something much higher dimension, right? So in this projection, it is an instant where it's possible, but actually, so here is a drive-by of another Penrose triangle, and you see now in 3D, of course, this geometry is not really possible, but if you have a 4th dimension, then there is one angle where it seemingly is possible in 3D, right? So this is playing with these higher dimensions. You can also generate impressions that seemingly are impossible. Now Penrose also introduced Penrose Flooring. This is an interesting tiling way, which is quite pretty, and this was actually used by Dan Shechtman to rationalize his idea of quasi-crystals. So crystals which do not have periodic symmetry, but which are still crystals. And so Schechtman got a lot of resistance for this, but eventually he was proven right and was awarded the Nobel Prize. So coming to the machine learning, really, we also have such cases, right? So here's a famous example from scientists at Google who applied at the time, one of the most powerful image recognition networks to this example of a panda picture. They added then a little bit of random noise to this, right? And so as a result, you would still, by naked eye, you as an observer would still clearly recognize the panda. The random, your brain filters out the random noise. These guys are hardly distinguishable for us. Now the machine, when you gave the random noise to the machine, it would think that this is some sort of worm, right? But with very low confidence. So that's okay then, right? But if you gave this mixed image, right, the sum of these two images to the machine, then with much higher confidence, the machine would predict this to be a monkey. And that's, of course, a dramatic failure, right? So adding a small variation then results in a hugely qualitatively wrong result. And that's, of course, a problem when you do image recognition, but also, of course, in our case, right? If we do a small variation in composition or in compound space, we don't want to have a hugely different response then. So this is something where we really have to be aware of this. And there are attempts within the pure learning community, the statistical learning community, to address this through adversarial learning, right? So these are certain strategies how you can make the machines more robust and less sensitive to such perturbations. But this was only recognized quite recently, right? So this paper was 2015, right? So this is one of the first to really demonstrate that this is a problem, right? So in some sense, you see that these are very new insights that I'm presenting here, and so there's not necessarily yet a good solution for all of this. So when it comes now to our problem, right, to our world, we have really a differential equation here, this eigenvalue equation, right, with an operator that is well defined, right, and eigenvalues and a state function. And so the question is, what we've discussed so far was the sort of alchemical changes and how things are connected with derivatives and interpolation. But the question is now, can we also tackle this this well-defined relationship using the statistical methods? And in particular, we have our nuclear charges and our coordinates. They show up in our operator, right? That defines our system. And then when we solve Schrödinger's equation, we solve that eigenvalue equation and we get out the property, for example, the energy. Now, if you have many examples of this, right, many examples of input-output pairs, right, then you can think of creating a data set and of training a statistical model on that data, which then you can use to predict these labels, the output labels for new input features, right? So we like to call in the machine learning lingo also input, we like to call that features. So the Hamiltonian is a set of features. and the expectation values is the output or the labels, right? So this is a problem known as supervised learning, right? When labels are available in your training data. There's also something known as unsupervised learning, which is when you basically don't have the labels, but rather you have only the input, but you presume that this input already implicitly encodes some information, some structure, and you'd like to, for instance, find out if there are certain clusters that belong together and so on. So there's some implicit information in the input features, and that you can also deal with, and that's typically called unsupervised learning. I put here a picture of a famous machine learning scientist, Vladimir Vapnik. There are many others, of course, as well. He's just one of them who really helped to put the field on rigorous grounds. This is, if you're interested in learning more about this, right, then you should look in the original machine learning literature. But he has a book called The Nature of Statistical Learning Theory, and a lot of these theories revolve around a method called Gaussian process regression, or also which results in under certain conditions also in kernel-rich regression, and these are models, statistical models, which have some relationship also to neural networks, and so from a pure statistics point of view, you can think of them all as regression models, right? So the particular form of your regression for the time being can be a secondary question. The important point is that you would like to have something like you see here on the right. Okay, so I think this is really an iconic picture, which helps a lot to get a good feeling on what is happening. So the idea is here that you have your label, right? So you have some function in the space of your input features, right? And what you're trying to do is that given, so, and this relates very much to Bayesian statistics. So given some data, right? Given some previous results, and this is shown here as these square data points, right? Given these data points, what is the most probable value of that target function in other areas, in other regions of your variable where you do not have data, right? So in this sense, it's an you can think of it as an interpolation method where you have data and you want to know results in between. But of course, this is a one-dimensional projection, and you can imagine as you add more dimensions, what does it really mean to be in between? Okay, so if you have two data points, it's clear it's in between these two. But if you have a one-dimensional, then it's in between the two. But if you have, let's say you have a triangle, 3 points in a higher dimensional space, then you could say, okay, a point that is exactly in the plane spanned by the 3 points would be in between. But what if you leave that plane a little bit, right? Could you still expect some generalization of the method? And that's the promise of machine learning, really, that the answer to this question is yes. So you can apply these models in an intermediate range in between extrapolation and interpolation. Right? So it's not an entirely binary thing anymore, right? In higher dimensions. Right? And so this is really, of course, if you go completely out of your data cloud and you predict somewhere where there's the next training data point is very far away, then you would call that extrapolation. But as long as you're in some vicinity with the other data points, you could call it interpolation. But so these words change a little bit in meaning. So what you see then is if the true curve, right, is the red one, and you only know about it, you have the actual numbers for it where you have the squares, and in between a statistical model could give you the dashed blue line, right, as the most probable in between value given all these other data points. And this, of course, implies also that you can construct something like a variance in between. So you have a window, right, where you know, okay, this could be some estimate of where the value could also be, but with a lesser probability. And so this probability, this variance, so in Gaussian process, then you would expect something normally shaped. But what's also very important to notice here is that the density of your training data, of course, has a huge effect on the error you make in your blue versus red curve, right? So where data points are close by, you can hardly distinguish blue and red. Where they are further apart, they deviate quite a lot. And you can also see that in certain regions, consider these 3 points here, right? Roughly speaking, they are at the same distance to each other, right? Now, in the right-hand blob, the blue curve deviates more from the red than in the left curve, right? And so the overall shape of your target function can strongly, even with constant data density, right, can strongly affect the performance of your statistical model, right? So these are things that are quite obvious when you look at this, and this should help you to measure your expectations in terms of how hopeful we can be to get decent predictions. So for us, this means that if we have some chemical compound space, right, which we would like to explore, you can quite easily generate target compounds, right? These would all be valid input features, and then you could select some of them to generate the quantum solutions, and by that you would have the labels, and then you can construct a model that would be applicable throughout. So you can view these data points like pillars on a bridge, right? So you need good pillars, right? But then you can have a nice bridge that gets you across. So in this particular case, in the kernel-rich regression, you can think of your actual model, so the statistical blue line here, in terms of a simple function like this. So this model gives you the estimated property of some molecule as a sum over the training instances. So you sum over all these squares, right? Each square gets a weight, and your query, when you come with a new molecule, let's say at minus 0.3 or so, then you have to measure the similarity of your new molecule to all the other molecules, right? So it's like a distance function which you use here, right? So how far away is minus 0.3 from these other data points? And of course, obviously, the data points at minus 0.1 and minus 0.5 are the closest. So the similarity function is close to 1, right? while data points out here are so far away that maybe they will hardly contribute, even though their regression rate might be very high, right? So this is maybe one of the simplest machine learning models you can think of. This is typically what's being referred to as a kernel-rich regression. You can get these regression coefficients here by a simple closed form equation. You invert a kernel matrix, which is the similarity function between all your training instances, right? So if you have n training points, you have an n by n matrix with a similarity function entries. You can regularize that matrix, but basically it turns out that to solve your regression problem, you have to invert it and multiply it with your reference label vector, right? And that gives you the regression coefficients. From this equation, you also see the units of your reference property gets carried over for your regression coefficients. And this kernel function, this similarity measure, is a unitless scaling function, typically between 0 and 1. Now, you can view neural nets, as you might know, they can consist of multiple layers of nested polynomials. If you decide to have only one layer, right, then this is closely related to such a kernel-rich regression. In particular, if that layer has as many basis functions or as many neurons as training instances, right? You also see that this sum here runs over your training instances, right? So the more training data you have, the more terms you have in your model, right? And this guarantees basically for every new training instance, you inherit a new regression coefficient, right? So this means that you can fit your training data perfectly, right? So in this sense, you can think of this function as an interpolator, right? You have zero training error. So the blue curve here goes exactly through your training point. While, of course, you have a prediction error in any query instance that is part of testing, not part of training, right? So when I make a prediction here, I can compare my prediction to a hold out label entry, which I did not use for training, right? For instance, this example, we said minus 0.3. So suppose I kept this red point here secret from training, and then I compare this distance, right? And that's the prediction error. And that's, of course, it's also known as generalization error. That's, of course, the error we are interested in, right? We want to make use of this to make new predictions for which we do not wish to solve Schrödinger's equation ourselves. So we need to know how well the model does. All right, so here is an example of how we got started. This is the GDB data set. It's a list of organic molecules, which was published by the organic chemist Jean-Louis Raymond at the University of Bern in Switzerland. Starting 2005, they have multiple generations of these libraries. And this is a bunch of smiles strings. So a smile string is basically a letter string with the graph information of an organic molecule. So it does not account for the 3D coordinates, just for the covalent bond connectivity information. So you could not distinguish conformers, for instance, right? But typically we do not distinguish conformers with a smiles string, but you can compare different compositions and different connectivities of molecules. And as the number of atoms in your organic molecules increase, the number of possible smiles strings also grows, of course, rapidly. And this is what you see here. And in our first attempts, within our first attempts to apply machine learning to quantum chemistry, we drew a set of smile strings from this library. Okay. And we then use this to define a training set for which we did quantum calculations, and a test set for which we also did quantum calculations. And then after training on the training set, you can then use the model to make predictions for your test set. And these predictions can be compared then, of course, to the quantum properties. Now, we started out with something which we call the QM7 data set. So we went up to 7 heavy atoms, not counting hydrogens. And there's roughly something like 7,000 molecules in here. This is what you see here now. These are the quantum properties which we calculated, and every dot in these panels corresponds to 1 molecule. Okay? This is a simple scatter plot of property versus property. Right? So on the diagonal you have identity, but you see that some properties are related to each other. So for instance, this property here is the ionization potential, right? IP. And as we discussed in our quantum chapter, right, there's some relation to the HOMO eigenvalue, right? So this is something you see manifested here by the numerical solutions. This is the electron affinity, which is also supposed to be related to the LUMO, right? And you see some relation here. Now, we have some properties occur more than once because we treated them at different levels of field. Right? So we also discussed that in the quantum part. You do have different ways to approximate Schrödinger's equation. So G stands for GW, HOMO, P stands for PBE, so this is a density functional value, and Z stands for ZINDO, which is a semi-empirical quantum method. So they are ordered in a decaying order of the kind of accuracy you would expect. You see often good correlations for the semi-empirical ones, and this is quite interesting, right? They are very approximate, and they meet these relationships more easily than the actual or more realistic estimates of Schrödinger's equation. Now, in this paper, so we first demonstrated this, that you can machine learn this in a PRL published in 2012. The original, if you look at the archive, the first draft was posted in sometime in summer 2011, which was after a long program at the Institute of Pure and Applied Mathematics, which I had organized in the spring 2011. So during that program, we did this, and then the actual paper came only out in 2012. We then quickly also used the neural net to repeat this sort of exercise on the data shown here, and that's this new Journal of Physics paper from 2013. One interesting thing then was to see if the neural net would exploit some relationships between these labels, right? So this is a multi-property neural net, and so if you use the quantum chemistry to get all this data, and then you naively plot the HOMO eigenvalue versus the energy, for instance, you seemingly get zero correlation, right? But now remember the case with these dimensionalities we discussed before, right? In particular, think about this one. This is how it looks like, but maybe there's a higher dimension, right? Which we are not taking into account. And that's exactly what you see here. We did a PCA on the coefficients in the neural net, and the first two principal component axes, 1 and 2, if you add them to this, right? So we basically add these 2 additional dimensions. This is then how the data looks like. And all of a sudden, you have a very nice, smooth and monotonic behavior. What you're seeing here is the energy axis. So this axis as the third axis in the cube, and the color code corresponds to the HOMO eigenvalue. Right? And now all of a sudden you see a very good correlation. And this is an underlying correlation in the high dimensional space of chemical space, which the neural net exploited when training. Okay. So this is exactly what you're hoping for when making use of these statistical methods, that they can exploit such implicit correlations which are difficult to spot by naked eye. Another important thing, again, connecting back to the biasing, if you take the naively just the compounds in GDP and you look at them in terms of their stoichiometry, right? Then you could, for instance, take the subset of all the hydrocarbons, so only carbon and hydrogen in the composition. Now, this is how the energy looks like as you look at QM7, right? And what you see are these plateaus, right? So this is not a normal distribution, right? And you've seen something similar in our alchemical predictions for these coronine molecules, where you have these spikes, these plateaus, these steps in the energy, and we ordered the energy in ascending order. And this is exactly what you have here. Every plateau corresponds to a different stoichiometry. Okay? And then within each plateau, you have the different connectivities. Right? So you have a separation of scales. And on each scale, you have a different number of possible compounds. And so if you think again about Bayes' theory, right? If your prior is not equally distributed, right? Then you cannot naively compare them or use them for training, right? You first would have to stratify things, right? So obviously, if you draw at random from this distribution for training, your regression model will be performing best where you have most data. Right? And so it will be performing best in this energy interval, and it will perform worst in up here at -20. You cannot trust your model, right? And so this is, of course, something you have to be very aware of, right? That the underlying training distribution matters, and we'll be coming back to that later on in the last sub-chapter in this chapter on the question of how you select your models. So here's another example. Actually, this was a machine learning paper. My first machine learning paper actually was published in 2011. We did that work in 2010. But this was sort of preliminary. But what we did here was to look at polyaromatic hydrocarbons. So all sorts of graphitic-like molecules, and we looked at reorganization energies, right? So that's an energy, the energy differences due to geometry relaxations with varying numbers of electrons. And this reorganization energy, it depends on something called a transfer integral and something called a transfer rate. And you could see then that the distributions look quite differently, but in the end, you can make use of such distributions to bias your training appropriately. So you can stratify things by saying, okay, I draw also here. I draw from each energy window. I create bins, and from each bin, I make sure I get the same number of compounds. Like this, you have a consistent predictive accuracy everywhere. Now, as you know, this field is very broad, and I can only talk about really some applied machine learning, some machine learning applications to our problem of navigating compound space using quantum mechanics. But there's much more behind it, of course, and there's also proper statistics behind it. And so if you want to dig deeper into this, I would recommend, for instance, this book by Rasmussen and Williams. There is, I believe there's a free copy you can get. And more related then to our field, there's this book, which we published recently with a whole bunch of contributions, which I can also recommend, of course. But there are many more. By now, there's a lot more overview literature. So also many reviews have come out over recent years. So I would recommend looking those up as well if you wish to dig deeper, and in particular the references in these reviews. Okay, so I'd like to now talk a little bit about this interpolation, right? And this is really something, of course, which did not start with Facebook, right? This is much older, and so it depends a little bit how you where you draw the line. There's some arbitrariness and how far you can go back and be of the opinion that this is still something related to machine learning. But these are keywords. If you want to dig deeper, I would recommend checking out, right? So inverse distance weighting, Shepard's interpolation, Kriging, Gaussian progress, regression, Bayesian inference, covariance. These are all valuable keywords. They all, in one way or another, deal with some problem like this. Okay. And now we, of course, have our binding curves, right? And so we know typically the ranges which we want to cover, right? So this is we do not only have this rigorous causal relationship as manifested by the laws of physics, but we also know quite well the range of our space. So chemical space is huge and high dimensional, but we know the periodic table is also finite, right? And the number of atoms are also finite, right? It's not infinite. Right? And so we know that there are some boundaries which beyond which we are not really interested. Right? So that is something that is important. And so we want to cover certain geometry, certain interatomic distances, right? And we want to cover certain stoichiometries, right? That reside in these trends. And then at some point, we don't need to go beyond, right? You don't need models that go below the strongest chemical bond you have, right? That's not necessary. So again, there's a little bit this chemical compound space, right? We have our dimensionality and then geometry and nuclear composition, and so we know the equations we have. Now here's an example of a case where things are much worse. So this is an overview of Switzerland, and these dots are the weather measurement stations. Right? And so given the data measured on these dots, you would like to interpolate the weather in between the dots and also extrapolate in time, right? So you have a spatial and time interpolation. And so you typically have time series on these. And so these kind of methods are being used for this, of course, right? Now, here is a bunch of faces from people who in our field of atomistic simulation have contributed to machine learning for the acceleration of our simulations at a quantum level. So one of the earliest contributions was by Bill Noyd and Bobby Sumter, neural net for potential energies. There are even studies from the 80s already that also make use of machine learning, but rather in the experimental sciences. So specifically to apply machine learning to atomistic simulations, I believe this really only started in the 90s. There are more papers in the 90s, but we skip ahead here to the 2004 at the Fritz Haber Institute. People in the group of Matthias Scheffler did some neural networks for surface reactions. Sergey Mansos and Tucker Carrington, they use neural networks for potential energy surfaces of small systems to get highly accurate spectroscopic predictions. And then very important, Michele Parinello and Jörg Behler, who used to be in Bochum, he's now professor in Göttingen. They presented a very nice generalization of neural networks, which made these models much more efficient and applicable for the study of potential energy surfaces. Now, it's important to highlight that all the papers I'm talking about here, with the exception of Kieron Berg, they are meant to interpolate for a given system. So the kind of interpolations they have been tackling were for geometries, right? So for fixed nuclear composition, and typically even for fixed constitutional isomers, so for fixed connectivity, right? So no reactivity yet. But then you have Gabor-Zany, who in Cambridge and with many co-workers, they developed a Gaussian approximation potential. So these are these kernel-rich regression models, where as a kernel measure, you use a Gaussian function. So you approximate your function by a sum of Gaussians, right? And that's something we all like to do. So it's very plausible, and that was a great success as well. Graham Henkelman in this program I organized at the Institute of Pure and Applied Mathematics. Graham Henkelman and Kieron Berg, they were both participants, and they used machine learning models then to optimize transition states as well as density functionals. So with these transition states, of course, you can then tackle chemical reactivity. And with density functionals, of course, you can also navigate chemical compounds. And so our contribution then was to say, okay, we want to really use this to sample the entire chemical compound space, right? And in terms of machine learning models, we've been looking at kernel-rich regression as well as neural networks now. Now, there's also a distinction that is made between these. So typically we call kernel-rich regression non-parametric, and we call artificial neural networks parametric. So that means basically that the number of coefficients you have in your model, if it grows with training set size, right, or if it becomes a variable, right, as your training, as your data changes, then you call this non-parametric. And if it's fixed, then you call it parametric, right? Now, the parametric case is the more usual, the more common case you learn in your undergraduate studies when you learn about regression. You have some fixed functional form with a fixed number of parameters which have to be fitted to some data, right? And as your data set changes, these coefficients, the number of these coefficients, the functional form of your regressor does not change typically, right? Now, this is where typically kernel-rich regression departs, and it adds additional coefficients as more training data is available. So here's we discussed kernel-rich regression already. Here's the typical picture, or one of the typical pictures of a neural network. So you would have these nested polynomials, right? So this would then be something like your model function. And you can view this as different nodes here that connect to other different nodes in different layers, and they can also couple back again, and so they're intriguing different architectures. You can imagine here how you connect these nodes, but at the end you would predict your label, right? So this is a picture here from this paper, but Jörg Behler in 2011 he wrote also a nice review. I would recommend it if you wish to dig deeper here, but there are also more recent reviews by now. Right? And in this new Journal of Physics paper, we also made use of actually we made use of a neural network with multiple outputs, right? So that we would exploit underlying correlations between these properties. So the picture that really emerges is that you have a chemical compound space which is high dimensional, right? And we map each compound to a point, right? And for those points where we have training data, we can span this compound space with the instances, and this is encoded in this kernel matrix, right? And then we can invert that matrix and get coefficients for every training instance. And when you make a prediction, you're collecting from each of these vertices. You collect the contribution, right, in the kernel-rich regression as a simple sum over these vertices. So if we want to do this, of course, we have to address this question, right? Which regression method should you pick? Which basis functions? What are the representative variables, right? What are the best features? How do you represent your compound? And how do you define this space, right? That is crucial because, of course, that will then define what are the similarities, what are the distances between the compounds, right? And also how you measure these distances. There's also a question, right? This is not obvious, and there are multiple possibilities for this. So here's just as an example, what we did in the past, we simply said, okay, our kernel function is now a simple Gaussian function of a distance in the high dimensional space, in the high dimensional chemical space, right? So this is a scalar distance, which we can have for any compound pair, right? Of course, if you have a Gaussian, you have a certain width. And so we took, this width is a hyperparameter, which you can optimize to your entire training data set as well, right? So there are procedures for that. And then maybe the most crucial question at the time was how do you represent your compound for chemical compound space? Of course, you could simply put the external potential from your Hamiltonian. Right? That would be your 3D function, and that would represent your compound in a unique fashion. Now, at the time, or still now, there has been a lot of precedent work using machine learning in the field of quantitative structure-activity relationships or quantitative structure-property relationships, which, as they are used in cheminformatics and bioinformatics methods, mostly for pharmaceutical research. But the kind of representations that have been used in that field, they do not match entirely to our QM, with our QM attitude, if you wish. So we had to come up with something better. One proposition, for instance, was that one could use electronegativity of the atoms, right? And if you look at the electronegativity for the periodic table, it looks roughly like this. And so you see carbon and oxygen, they have different electronegativity, and so the machine learning model could distinguish them. But then you notice also that carbon and chlorine have very similar electronegativity. Right? Now that's very problematic because obviously these two elements have very different chemistries, right? And so if you represent them simply by their electronegativity, you're implying that they have a similar effect on your energetics. That's certainly not the case, and so this is problematic. In this sense, this representation here, this electronegativity descriptor, is not a unique thing, and so it might be problematic when trying to learn the quantum energy, right? And so the question is really how do we represent a compound, right? And this comes to the core of this course, right? What is a compound really, right? Now it is the external potential, and that is certainly true, right, from the quantum mechanics. But that's maybe not the best way to build a statistical model, then, right? So is there something that makes this representation more compact, more unique, more versatile, more efficient, more pronounced in strengthening those aspects of the external potential which really matter, rather than sort of diluting the information in a lot of redundant data entries, right? And that might make it for the machine much more difficult for the machine to extract the actually dominating factors here. If we look at Schrödinger's equation, right, it's clear that it must derive from nuclear charges and coordinates, right? And you could think of a simple array, a vector, right, encoding just for every atom the four variables: nuclear charge, x, y, and z coordinate. Right? That would be a unique representation. From that, we can construct any Hamiltonian, and so that uniquely determines our energy. The desirable representation should be unique. Two different compounds, right, should be possible to distinguish them, but also it should be translationally invariant, right? At least for certain properties, right, or for certain systems. So for molecules, for instance, your quantum expectation values should not change if you translate your compound around. And it should also be rotationally invariant. It should be, ideally, it should obey the symmetries, right? So you have symmetric groups in the compound and you flip them, right? You'd like to have the same representation. No, that's not true for XYZ coordinates, right? So this is, I mean, in particular, the translation and rotation, they would change these entries, right, if you use XYZ coordinates. You ideally would also like to have a constant length, right? In some sense, if you map out the external potential and you assume a certain box in which your whole thing fits, right, then the length of this potential will not change as you add more atoms or electrons, right? Or imagine that your nuclear charges grow, right? You get more and more electrons, but your representation should be the same, right? It shouldn't grow with this. So that would be very convenient, right? And you would also like to have some permutational invariance. So the fact that one atom is mentioned first does not, or second or last, should not affect your quantum property. And so a good representation would not include this dependency. So one thing, one proposition which we came up with in 2011 was this Coulomb matrix, right? So the Coulomb matrix is an atom by atom matrix. On the diagonal, you put a formula that depends just on the nuclear charge. This is an expression that is similar to a free atom energy expression, right? So we discussed some expressions like this for the energy of the free atom. It should really be not, the exponent should really not be 2.4, but rather 7/3. So 2.33 would be a more accurate model of the free atoms energy, but still, so this is a reasonable thing here. And on the off-diagonal elements, you put the nuclear repulsion between the atoms. Now, this matrix is unique in the sense that if you have two different molecules, they will always have different Coulomb matrices. It's translational and rotational invariant. It would account for the symmetry, so you would get the same entries. And if you have systems with different sizes, you can always pad the matrices of the smaller molecules or compounds with 0. Right? And you can make it index invariant by simply sorting this matrix, or by diagonalizing using its eigenvalues, or by also another way would be to have multiple permuted matrices and use this the set of matrices as a representation. So these are all ways to sort of more or less encounter or meet these conditions. So in my mind, maybe the most important one is the one about uniqueness. Right? If you don't have uniqueness, right, then to the extent that properties between systems that happen to map on the same representation, to the extent that these properties deviate, you will have to be satisfied with the resulting residual error level in your model. So your model cannot possibly become more accurate than that remaining deviation, right? And so depending on the lack of your uniqueness, that deviation can be quite substantial. So for a molecule like ethylene here shown on the left, the Coulomb matrix might look like something like this, right? So for the carbon atoms, you have big entries here, carbon-carbon repulsion, right? Big entries, carbon-hydrogen repulsion, big entries, and then the hydrogen-hydrogen repulsion and hydrogen contributions are the smallest entries. Right? So it's a very intuitive thing, right? You can just by a mere inspection, this all makes sense. And so our expectation that maybe this is not the best model, but it definitely must work if we can make use of supervised learning. This is what motivated us to propose this and try this. So as a Euclidean distance, as a distance in this Gaussian function, we decided to just go with the Euclidean distance. So this is the L2 norm. And with this, basically, you then have defined everything you need in order to train a kernel-rich regression model. Okay? So you need to define a kernel function, a representation, and a matrix. Right? So once you do that, you're good to go. And well, of course, you also need the data, right? So as I mentioned before, we had this Qn7 data set, and we did DFT calculations on them. So this is how the energy looks like as a function of the Coulomb matrix Euclidean distance. Okay, so this D now is this D where the M matrix is defined up here. Right? Now there's a huge gap here, and you might wonder, what is this? It's very easy. These are molecules. Let me see. Yeah, this is shown here also. Your now it's not your energy, but the frequency, right, in the data set. What you see here are distances between molecules where all elements come from the second row in the periodic table. And here, this bulb here corresponds to molecules where one of the atoms comes from the third row, in particular sulfur, right? So we had sulfur and chlorine in this QM7 data set, and this results in the Coulomb matrix in a much larger distance. And so this is where this comes from. Okay, so the loss function can be written in this way in kernel-rich regression. So for the training set, we have the reference data, and so you fit the deviation of your model to the reference by squaring this, and this is a regularizer. This lambda value is typically very small, and so you can show that with an Euler equation, right? If you minimize this in your alphas, you must get 0, and then you solve for your alphas, and you get this expression, which tells you have to invert that kernel matrix to get your coefficients. So we use again this kernel matrix, right? Now the hyperparameter sigma here and the lambda has to be optimized, and the way you typically do this is with what's known k-fold cross-validation. Now this is a standard procedure also to protect yourself from overfitting, and so I would strongly recommend you always do this by principle. The procedure is very easy. You divide your training data into k blocks, and you predict each block as a holdout block with the models trained on the remaining blocks. And so then you can average the mean absolute errors over these holdout sets. And in particular, you can then use this error to minimize it in your hyperparameter. So until your hyperparameter is converged, you can run over these over this cross-validation. If you have 2 hyperparameters, then you will need 2 nested loops, right? So this is a little bit of brute force method, but you can apply more sophisticated optimization algorithms also to it. You see that the more hyperparameters you have, the more painful it gets. So it's also, it's not only convenience, but also by necessity that we assume a width that is constant for the entire data set. But this is a well-approved method, procedure, how to deal with these additional parameters. Now, once you've done all of this, you can apply the resulting model, right, the optimal model then to measure your error on test set on test sets that were not part of the cross-validation. Right? So that's the true test. Right? So the model has never seen these test points, and so this is after you've done this training. This is then the test, the query which you want to do, and so you make a prediction, and then afterwards, after you've done your prediction, you compare that prediction to the true value. And that is the prediction error, or the generalization error. And you see this error here for the QM7 data set as a function of training set size, and it comes systematically down. Right? So this is really, this figure was the figure that convinced me really that this is exciting and that this has some promise. The point is, of course, you're making now a prediction here of the reference energy, let's say the DFT energy of a new query molecule, and that prediction takes just a millisecond. Now, of course, you can only do this once you've trained on it. So it's not a free lunch, right? You had to have the training. But once you've done this training, so the cost, the computation cost is shifted up front. First you train, first you need to acquire the training data, and then you train on it. But once that is done, you can predict arbitrarily many compounds at millisecond speed, right? And as long as you're not, as long as the query compounds are represented by your training data set, so as long as there's some reasonable similarity, you can expect a deviation from the true DFT energy that systematically decays as your training set increases. And so this is something, I mean, we've discussed these approximations and quantum methods, that is in some sense a paradigm shift, right? Because that allows you to systematically approach a certain level of error through mere addition of data, right? So the physics does not improve as you increase your data set, right? You simply, the only thing you do is you add more, you increase the density of data around your queries, and that improves your model. And so that's something incredibly powerful. Of course, it's also dangerous, right? Because you might be tempted to believe that we do not need to know anymore about the underlying physics. But that is, I think, it's a tempting, but it's a wrong conclusion, right? It turns out these models become much more efficient if you account for the right physics, and so maybe not surprisingly so, it always helps to understand what you're doing. In this in this paper, we reached prediction errors of 10 kcal per mole, which is roughly the error in atomization energies you would make with the GGA functional. And so this basically means if you're training on a GGA, it does not make sense to go beyond 5,000 or so training molecules, right? Then you are as good as a GGA in terms of a comparison to the reality or the true values. And so this is big news, and what was big news 10 years ago, and so this is what created in terms of machine learning predictions of quantum properties across chemical compound space. It really gave a reason for an entire field by now to emerge. You can see here a scatter plot of the estimated atomization energies versus the true estimation energies. This is in, you should note this, this is in mega calorie per mole. Because of course these molecules have different sizes, right? And so each bond is 100 kcal per mole, and so the range is from 500 to 2000 kcal per mole. So this was another important insight or take-home message which we got during this study. If you took any one of these data sets and you calculated the correlation coefficient, it was very close to 1 for all of them, hardly distinguishable. And that is due to the huge scale on the units of these axes. So this correlation coefficient is really to be used one has to be very careful when you use it for comparing different models. At the end, I think a true error estimate, true error calculation is much more meaningful. You see here comparison also to bond counting, right? And to a semi-empirical quantum method. And most interestingly, right, as your molecules become bigger, you see that the semi-empirical methods and the bond counting, they fail to incorporate the non-local effects of quantum mechanics, right? While the machine learning model does account for them. We have a unique representation that accounts for the full quantum problem. And so if your model is trained well enough, you must be able to capture these effects. So I'd like to still address one frequent point before calling it a day today, and one important point in the understanding of what we are doing here. There's something, as you know, hopefully very well, called overfitting, which can be a real problem. Now, how do these models, right, with 5,000 training coefficients, how do they deal with overfitting? And so here's a way to view this, right? So traditionally, if you had a certain regressor function of a fixed size, okay, and of a size which is too small, right? It's not flexible enough to really fit your data. Then you would have something called an underfit, right? So here you have some linear function, and in red you have the data, right, of some label with some variable, and so this is just the best compromise you can get going through all your data. Right? So your error is the deviation, the loss here between your model function and the true data. And so your training error is quite large, right? And your prediction error, if you imagine that you you simply interpolate here, your prediction error should be similar. Now, if you have a more flexible function, it might look really, really good, right? But you notice there's still some deviation. So the training error is still non-zero. And then if you go to too large, too many terms, too many coefficients, then you fit exactly through the data. But the shape, just from looking at it, it seems to be very likely that it's overfit. Actually, I should remark on this, that we do not know if this is overfitting or not, right? If by looking at the right-hand side, you are convinced that this is overfitting, I'd like to ask you to revisit this premise. Actually, we don't know, right? It could be that the actual function just looks like your model, right? You just don't have data, right? So it could be overfitting, but it could also not be overfitting, right? We don't know. But suppose it is overfitting, right? What you really have then here is something like this, right? And this is now an important distinction. I'd really like you, if you haven't thought about it this way, I think this is really crucial to understand machine learning. You must distinguish between the test error and the training error, okay? And so you see these two errors shown here in red and in turquoise. So in the underfitting regime, your test and your training error is high. This is what you see here, right? In the overfitting regime, which we assume now is overfitting, so let's assume that the true function looks something like this, you would observe this kind of scenario where your training error is very low, you fit through all your data points, but as you start measuring new query data from in between, you see that the error is larger than in the middle point, right? Where your prediction error for new query points is quite small, right? And so in terms of your test error, there is some optimum, okay? And this is true for any parametric model. In a parametric model, there is an optimum somewhere, might be beyond your numerical precision, but it is there, mathematically speaking, where upon inclusion of more data points, of more testing points, right, you would go up again in your error. In the case of kernel-rich, of a non-parametric model, such as kernel-rich regression, you do not observe this, right? The training error will never go up again, okay? Now, this is a fundamental difference, right? And the reason is that it's not parametric, meaning as you add more training data, you become your prediction error must systematically decrease. Your test error must systematically decrease. So in some sense, you have in the traditional model, you're finding the best compromise. In a non-parametric kernel-rich regression model, you go exactly for the points. And again, you get this kind of picture where you can imagine here, as you increase the density of training data points, right? That's what's happening as you increase your training data size. as you increase that density, the deviation, the variance and the deviation become smaller and smaller and smaller. And you can simulate that just by moving from areas with little data points to areas with many data points. You see systematically this comes down. Actually, there is a mathematical proof for this, which was given by Wapnick and others for these kernel-rich regression models or Gaussian process regression, but also for neural networks. You can show this if they are sufficiently large. You can show that you will always be in this regime here where the training error must come down. So this is what you then should expect, right? In a traditional fitting sense, as your training set increases, your test error comes down to that optimum, right? Your training error must go up, right? So as you add more training data points here, right? Your model in the traditional way is fixed, right? And it cannot improve anymore, right? So that's what you see here. So it does not improve anymore in testing and in training. In the beginning, if you have so few data points that your model with little flexibility goes through every training point, right? Then it's perfect. You have a zero error, right? So suppose you have a linear model here, right? With just 2 points, you have 0 error. But then you add this point all of a sudden, right? Then your model has to negotiate, right? And that's why your training error must go up then. Now, if you are in this regime, right, at some point, no matter how much more training data you add, your model will no longer improve, right? So the idea, the notion that the more training data, the better, that notion is only true if your model is good enough to make use of that data. If you choose a machine learning model, a more traditional one, then that's not necessarily true. At this data set size, right, you would not improve anymore, and it would not make sense for you, given that model, it would not make sense for you to look for more data. Now, by contrast, the non-parametric models and sufficiently large enough complex models, you can train them such that your training error is numerically 0, and you pull down systematically your training, your test set error. So this is the paper where the proof was given that the prediction error is inversely proportional to training set size, and this exponent b is if you logarithmize things, if you put this on a log plot like this one here, then you should see a linear function in the logarithm of your training set size, right? Where b, this exponent here, becomes the slope, and the proportionality constant a is the offset of this linear function. Okay. So in this paper in 92, Wapnick and co-workers proved this, and then Klaus Müller and others and co-workers in 96 showed that this also holds for neural nets if they are large enough. All right, with this, I'd like to conclude for today. Are there any questions? It doesn't.
I would maybe have one.
Sure.
And it's specifically on kind of, let's say, relatively simple linear models like convergent regression versus things like deep neural networks.
Yeah.
And what we've looked at so far is like mostly kind of here for chemical applications, like simple linear models. And okay, I mean, most papers shown are like now 10 years old. But it seems like a lot of work is still on relatively simple linear kind of regression models. Whereas in kind of almost any other application of machine learning, kind of people have started using linear models like support vector machines, and then all kind of recent successes have been achieved using deep learning. I mean, this holds for like speech recognition, image recognition, text generation, playing video games. Everything nowadays, kind of the fancy stuff has always been done using deep neural networks. I wonder, is chemistry just not far enough advanced yet that kind of these methods have come through? Or is there some fundamental difference why quantum chemistry might not benefit as much from deep neural networks as other fields?
So thanks. I think there's an excellent point, and I fully agree with this observation. There are very interesting deep neural network applications of chemistry too, but typically they perform well. So typically you always will find a kernel-rich regression model, or often you find a kernel-rich regression model that is among the best performing ones, best performing machine learning models as well. And I think one possible reason for this is that in particular when it comes to quantum chemistry, right? The problem is really a very well-defined learning problem. It's a defined supervised learning problem. And so we can incorporate our understanding and our knowledge much more easily in these comparatively simple, so you call them linear models, but it's not really a linear model. It's a linear combination of nonlinear terms, right? So this is what's also known as the Kernel Trick, right? So, but these simple, if you wish, you could view it as a shallow neural net, right? Just with one layer. So, not a deep neural net, but a shallow neural net. So you can it's relatively straightforward to incorporate that understanding in these models more explicitly. And then and we will show this later on, right? Then you can exploit that expertise more easily, I think, than in a neural net. And so the neural nets, they have this, if you're unable to do this, right? If you don't have this expertise, right? For instance, let's say playing video games or folding proteins, right? Like an AlphaFold, which is in some sense, it's much less well understood than our understanding of quantum mechanics, right? Then the neural network has to discover all of this. And that's more easy for a neural network than for a kernel-rich regression model, right? So I think that might be related to why we observe this. When we when we approach the machine learning from the physics point of view, we have this cultural attitude also that we want our models to be as simple as possible, but not simpler. Right? So that's something I would argue most physicists would feel quite strongly. And so it's also a sort of a game, right? If somebody needs millions of coefficients to make a prediction, can I make that same prediction with only a fraction of the coefficients? That's something that many would consider to be a part of our job, right? To go after this. So I would say there's also a cultural bias in some sense that we have always asked this question, okay, can we do this in a in a simpler way. That's something also our community rewards, right? If you manage to get the same answer with simpler model. While maybe in other communities that's not the case, right? So I think that is another aspect. So the first one is it's maybe more well defined. The second one, there's a cultural aspect, and the third one might be that our data is very expensive. Right? So typically, I mean, if you want to make a splash, you want to predict things where the data is expensive, and so data efficiency is really in the training is very important. And so when people train neural networks on millions of data points, that's really not so appealing for us, right? We would like to get away with much fewer data points. So I think it's these three points, they will contribute to this. Maybe there are more points, I don't know, maybe there might be something inherent, right, which we haven't realized yet, but that's what I would say.
Okay, thanks so much.
All right, so let's conclude. Thank you very much, and we'll continue next week, same time, with our last lecture this semester. All right, bye. Thank you.
Bye. Thank you.
Bye.